Here we go. Yep. Thank you, folks, for joining another session. So what we're going to do today is, in terms of breadth, I don't expect us to cover a lot of breadth today, but in terms of depth, we will be covering sufficient depth. All right. So we'll continue from where we left, which was logistic regression, and all right. So this is where we were. We were trying to calculate the partial derivative of the cost function, and the cost function is, this was a cost function, basically y log, this by the way is y hat, folks, plus 1 minus y log 1 minus y hat. So we figure out that the partial derivative of this function is the last row here, which is y hat minus y times xj. So that's the partial derivative. Now let me ask a question so that you guys wake up. Here's a question. Derive the partial derivative expression of the cost function with respect to b. So here we derived it with respect to wj. I want you to derive it with respect to b. How would you do it? I hope you understood the question. I just want the partial derivative to be derived with respect to b instead of wj. So just replace wj with b and see how the partial derivative calculation would work.
xj will not come in final answer.
Sorry, say that again.
Xj will not come in final answer.
Why?
Multiplied by x. When doing partial derivative with respect to b, we get in 1, 2, 3, 4. In fifth step, with respect to b, when we do partial derivative, here we get xj. But when we do with respect to b, we get 1.
Sorry, who's this who's answering?
So Rajeshwari.
Rajeshwari. Okay, all right. Can you explain it step by step? Okay, so can you see my mouse? You can, right? I hope you can. Wait,
Yes.
give me a
Yes.
moment. I'll just switch to. This is a presentation. I think I can switch to. Just give me one moment. All right. So this is going to be B now, correct?
Yeah. Yes.
Will this expression change, the one that I'm highlighting? Let's say I've replaced wj with b. Do you see any other change here? Let's say I've replaced wj with b. Do you see any other change? No change, right? Correct?
Yeah. No
Because
change.
all right. Now let's come to this part. Any change that you see apart from wj becoming b? This
No
row,
change.
no
No
change.
change.
Correct. This row, the one that
No
I'm
changes.
no change. Correct. This row,
It also has no changes.
no change. Correct. Now let's come to this row. What happens now?
Multiplied by xj, instead of that we put 1.
Why? Explain that.
When doing partial derivative with respect to b, b's coefficient is 1,
Mm-hmm.
and w1 x1 and w2 x2 are considered as constant.
Just one moment. Somebody needs to mute at their end. Is it your end, Rajeshwari? No, not you, Raji.
No, no.
Someone else. Who is it? Abhinav, can you mute? Abhinav, can you mute at your end, please? Okay, let me mute him. All right, he's muted. All right. Give me a moment, folks. So, okay, so what you're saying is this partial derivative, when it's with respect to b, what happens to w dot x?
It will become 0 as it considered as constant.
Correct, that is right. And then when you take the derivative of b with respect to b, that will be 1. So which means instead of xj, you would see a 1 there, right? So it's y hat minus y times 1. That will be the partial derivative of this expression with respect to b. Okay, right. Now, let me move to the next slide. The others. Okay. Now what we're going to do is we have this expression with us, and let's take an example as to how we go about updating these weights, and how we go about figuring out what is called as the lowest cost. Okay. Now, before that, I have a question for you. I don't want Madhumita to answer. I don't want Sandhya or Mugundan to answer. I want someone else to answer. You have a function. Just imagine a function. And then we know that the first order derivative is the slope. Can you tell me what does the second order derivative mean? It could be partial. It could be, say, a derivative which isn't a partial derivative. It doesn't really matter.
Says whether the curve is convex or concave.
Okay. Can we say it tells us the measure, the extent of curvature? Can we say that? So
Yeah,
for
we can say
example, I'll just clear this. So let's say I'm going to keep it simple. Now let us say I have a curve, something like this. It's not technically a curve, but let's say this is a curve. All right. Now between this point here and this point here, forget everything else. Is there a curvature there between this point and this point? Can we say that it's curved or is it flat? Between this point and this point. Forget the point where it bends. Let's say you've crossed that bend. Can we say it's curved or is it flat?
flat.
Flat. Okay. Now, in English, we say it's flat. But the question is mathematically, how do you say something is flat?
Slope is 0.
Slope is okay. Let's say it isn't exactly flat, but close to flat. Then, because even in my diagram, it isn't exactly flat. So let's say it isn't exactly flat, but close to flat. Then how do you, I mean, when you looked at the curve, you said it's flat, which is right. Or let's say you say close to flat, but that's English. How do you represent that mathematically? Any thoughts, folks? Just think about it. Okay, let me ask a question here. Where do you think this whole figure that you see in front of you is the most curved portion? Where do you see that? Which part of this whole figure is the most curvaceous part? Which part?
The two sides you have marked.
Louder, please. Sorry, say that again.
The 2 points where you have marked.
Exactly. Don't you see that this part and this part, these are the two places where this whole figure gets very curved, right? Now, Kyle, if you think about it, in this section, there is a slope, correct? There's a valid slope. It's a negative slope. Here again, you have a positive slope. But still, it's not curved, isn't it? It's flat. It's still flat. It's not curved, right? So curvature has nothing to do with slope being equal to 0. We just can't say that because here slope isn't 0. There is it's a proper negative value. Here again, you have a slope which is a positive value. But certainly this is not curved. Certainly this is not curved. So mathematically, how do we say that a particular graph or a function is curved? How do you say that mathematically?
Is that second order derivative should be equal to 0?
Is second order derivative should be 0 is that's for maximum. Okay, second order derivative should be 0. Why?
Because if we take a line which is a straight line, so it should not be equal to 0.
Okay, if it's extremely curved,
So
what happens? What happens to the second order derivative? If it's extremely curvaceous at a
slope will be high.
particular. Okay, sorry, say that again.
The slope will be high, right? If it's
Is it so?
extremely curved.
Will slope be high? Or will the rate of change of slope will be high?
Yeah, rate of change of slope will be high.
Right? So for example, at this point, look at this point, folks. This was a slope, right? So this is how your slope would have looked at this point. Now suddenly, the whole thing becomes flat. So don't you see that the slope has changed dramatically? Whereas if you take, sorry, this point and say this point, the slope hasn't changed at all, which is why we are saying that there is no curvature there. So the way to measure the extent of curvature is by looking at the second order derivative. If the second order derivative is high, then it's extremely curved. The curvature is high. If the second order derivative is low, then you can say that it isn't that curved. All right. Now let's go back to the Excel. So what we're doing here is we're taking a simple example. These are, I'm going to keep it simple. We're doing logistic regression. We have two features, x1 and x2. Y is the class of, it's the output. Takes a value of 0 and 1. I'm just going to derive a cost function using the first data point, which is this. So let's look at this. Here is x1, x2. This is y. I assume a value of w1 and w2 because I'm trying to optimize, so I'm assuming a value. Can somebody tell me what would z be? Let's go back to our understanding of. So let's look at the cost function. Here we go. This is what we were. This was a cost function that we were optimizing, correct? Right? Okay, now what is z? We derived it here, by the way. So what is z? Isn't it w dot x, the dot product of the weights and the feature vector? Can we say that? That's how we define z, right? Isn't it? Any doubts on that? Because if you look at the way we define z, z is nothing but the dot product of the w vector and the x vector. X being the feature and w is of course the weights. So we calculate z. Now, of course, in this particular case, z is actually wx plus b, but I'm not introducing b. I'm going to keep it very simple here. I'm assuming b is 0. So z, I'm keeping it as w dot x. All right. So here is z, w dot x. So can somebody, again, to wake you folks up, for this row, how do you calculate z? How do you calculate? I know the answer is 20, but how do you calculate? Take this row. I'm highlighting this row.
3 into -4 plus 2 into -4.
That is right. 3 into -4 plus 2 into -4 again, right? So that works out to -20 here. Okay, fine. So that's z. But then we know the partial derivative is you have to apply the sigma function on top of that, correct? All right. And that's y hat, isn't it? Y hat is sigma times, sigma of w dot x plus b. So here we go. We know the sigma function is 1 by 1 plus e power minus z, correct? If you still have confusion, sigma z equal to 1 by 1 plus e power minus z, all right? So that's what I've done here. That's y hat. I also have 1 minus y hat. I'm just making it easy for me, convenient, okay? Now, when we calculate the cost function, look at the cost function here. Can somebody help me to express this cost function in terms of y and y hat? Just make it convenient for me. Express this in terms of y and y hat. Look at the cost function. This bracket, this whole thing is a cost function, right? Which is what we took the derivative of the cost function. Can somebody express this whole thing?
Y
This
log
cost,
y hat plus
okay,
1 minus y into log of 1 minus y hat.
That is right. Correct. All that we have to do is sigma w dot x plus b has to be replaced with y hat, right? So it becomes y. Of course, there's a negative sign there. Y log y hat plus 1 minus y log 1 minus y hat. All right. So what we've done, okay, question again. I'm calling it log, but the moment we talk of logs, base is extremely important. What base is this?
10.
Think. Remember, Rajeshwari, was it you?
Yes, please.
Okay. Derivative of log x. What is it? The first
1 by
derivative.
x.
Okay. What is the
Oh,
assumption there?
log e.
What is the
Log
assumption there?
e.
Okay. Sandhya says it's e. But what's the assumption there, Rajeshwari? Do we assume it's log
Base
10? When you calculate log x is equal to 1 by x,
No, it's e. Base e.
it's e, right? So don't you see, you actually use that function here. Don't you see that? You calculated the derivative of log. So what do you think should be the base of this log?
It's e.
E, correct, not 10, right? Though it's just a scaling factor. You can always convert from e to 10, 10 to e, that is easy. But it is not 10, but it is e, okay? Fine. So what I've done here is, so we know log, if it is to the base e, we call it ln. So what I've done here is I basically calculated the ln of y hat and the ln of 1 minus y hat, which is the same as log of y hat and log of 1 minus y hat. Okay. Now let's look at the gradient here. Now there are two features, W1 and W2. Can you tell me how many gradients are we going to calculate?
Two is in this case.
Correct. Two. Yeah, because there are two features, right? So you're going to calculate two gradients. Now the first gradient, just help me express this. So what does this mean? I already have an expression which says the partial derivative of the cost function with respect to Wj, let's call that W1, is equal to this expression. Can you help me interpret? Let's say I want to calculate one of those gradients. How will I calculate it? Help me look at this expression and then help me calculate the gradient. How would I calculate it? Mugundan, you're not very audible, Mugundan. I'm sorry.
Y hat minus y into x5, x1.
Okay. So y hat minus y multiplied by x1, correct? And the other gradient? Y hat minus y multiplied by x2. Would you agree?
For
Mukundan?
second gradient is
Second gradient. Okay. So that's what I've done here. So here we go. I have calculated y hat minus y multiplied by x1, y hat minus y multiplied by x2. Okay. I've also calculated something called as gradient norm. I don't want Mugundan to answer. I don't want Madhumita and Sandhya to answer as well. But what do you think is gradient norm?
Average.
Raja, you were trying to answer? Were you?
Average of two gradients.
It's a norm. What does norm mean? Okay, let me try to explain, okay? So let's say you're trying to, you're descending a hill, down a hill, and you want to hit the valley. Okay. So when you're doing that, imagine yourself to be, imagine yourself to climb down rocks. So you walk a little bit in some direction, then you climb down a rock, so on and so forth. So when we say gradient of x1, it is, imagine yourself moving in a certain direction, and gradient of x2, just imagine yourself moving in a perpendicular direction of x1. Okay, just imagine that way. Now, of course, while you traverse from, say, a hill down to the valley, you would move in various directions before you reach the valley, which is what we're attempting here. We're trying to reach the valley here, correct? And you need a measure that helps you to calculate how much you have moved. So for example, I'll take an example here. Again, we'll keep it simple. In 2D. So let us say I start from here and eventually I move here, which means I have moved so much in the y direction and I have moved so much in the x direction. Now I need one measure that helps me to determine how much I have moved and in which direction. What would that measure be? Or let me put it this way. I need one measure that tells me how much I have moved. What would that measure be?
We take the x and y distance as two sides of a triangle, and the hypotenuse will be the distance.
Exactly. So this is the hypotenuse, correct? So can't I say all that I need is, I need this distance, correct? So square of this, sum it up and take the square root, correct? And now if you think about it, that's exactly a norm. That's the definition of a norm. So what I've done here is I've calculated a gradient norm, which is to say that, look, see, it's quite possible that I may not have moved in one direction, but I might have plunged completely in another direction. You getting what I'm saying? Let's say I'm climbing down a hill and then I don't move in this direction, but then suddenly I slip. And let's say this is the valley. This is the point that I want to come. Okay. I want to reach this point. I'm here. Now suddenly my legs slip for whatever reason and I plunge all the way down to this point. So if you think about it, I haven't moved at all in this direction, but I've made significant progress in this direction, isn't it? So what the gradient norm measures is the combination of these two factors. The fact that here I could have moved in this direction, or effectively I could have moved in this direction. And I need one single measure that, that measures that movement in both directions. And that's what gradient norm allows us to do. All right. Now just think about it. I'm going to ask a question. So let's say this is the valley. And I'm almost there at the bottom of the valley. Kashmir Pallathakal now on that chip. Pallathakal irukanapo. Now, of course, the gradient is still valid. I could still move in X direction and Y direction. But can you tell me what would the norm be now? The gradient norm? intuitively. Because your objective is simple. You want to reach the bottom of the valley. That's the objective, which is this, the lowest point in the valley. Now you're coming close. You're somewhere here. You're somewhere here maybe, or here. When you're there, my question is, what would the gradient norm be? Do you expect the norm to be high, or do you expect the norm to be low? What do you expect? When you're close to the valley, I mean, the lowest point in the valley, let me put it that way. Remember, the objective is to reach the lowest point. Once you reach the lowest point, you're happy. You're not going to roam around. Let me make it very clear. நம்ம இலக்கு வந்து அந்த lowest point வந்ததுக்கு அப்புறம் we are happy. முடிஞ்சதுடா வேலை அப்படின்னு நம்ம ஜாலியா இருக்கும்.
Norm would be high.
Why would the norm be high? That's my question.
Yeah, trying to reach the lowest.
Correct, but I'm already here. Or maybe here. I can understand if I am here and if I'm plunging down, norm will be high. I can understand that. But I'm saying I'm already here. Close to the, the bottom.
Then it will be minimum.
Exactly. So in a way, when you reach very close to the bottommost part of the valley, your norm would be minimum. The gradient norm would be minimum, because there's nowhere to move anymore, because you're close to the lowest point in the valley. And that was the end objective. Your end objective is not to get to the lowest point and start climbing, right? Your end objective is to get to the lowest point in the valley and stop there. Now when you're very, very close to that point, the gradient norm is expected to be very low, right? Because there's nowhere to move anywhere. You kind of stop, literally. Maybe you can move your leg a little bit here, a little bit there, maybe a little bit above, a little bit below, whatever, but there isn't much that you can do at that point. Okay. So at that point, you'll find that the gradient norm is the minimum, literally, or close to zero, perhaps. All right. So next thing is we determine the cost function. Now, can somebody tell me, just look at this and tell me what is a cost function? Express it in terms of y and y hat. I know we have done that even a short while. We did that even a short while back, but let's do it again. What's the
Y
cost
log
function?
y hat plus 1 minus y into log 1 minus y hat.
And there's a negative sign outside, correct? That's there. Don't forget that. There's a negative sign. All right, fine. Okay. So which is what I have done here. So if you look at this expression, folks, there's a negative sign outside, and then I'm calculating y times ln y plus 1 minus y, sorry, y times ln y hat plus 1 minus y times ln 1 minus y hat. Okay. The cost diff is nothing but as my cost changes, I'm calculating the difference in cost. So this is nothing but the current cost minus the previous cost. Okay. Then I have one function called the lowest cost. What it does is, so there are 50,000 rows here. It just calculates the lowest amongst that lot. Okay. Ignore cost minus lowest cost. It's not particularly important. Now, learning rate. I want somebody to tell me what do we mean by learning rate? So let me take you to the relevant slide and now tell me what is learning rate and what does it tell you?
The size of the step we take that
Okay,
inside.
the size of the step. Now, what happens if, so let's say I'm here. What happens if the learning rate is huge?
There is a chance we
means the
cross
minimum.
local minimum.
Okay, yeah, Rajeshwari, you were saying something. Go ahead.
There is a chance that we cross local minimum.
Okay, if you look at this line, and I'm trying to traverse, I want to get to this point. Okay, I'm at this point now. I apply this logic. This was a previous weight minus eta, which is the learning rate, multiplied by the derivative, correct? Of course, there's no partial derivative here because it's a simple example where there's just loss and one feature. But let's say my eta is huge. What happens? Where will I go from here? I'm starting here. Where will I go? Or where will I lie? Let me put it that way. I don't know where I'll go. I'll go somewhere, but where will I lie? Will I be on the curve? Where will I be? What does
You may
this
jump to the next side of other side of the curve.
other side? Is that so? Not necessarily. I mean, let us say this is, don't worry about that bit. Okay. Let's say I'm moving in the right direction. Okay. I've gone one step down in this case. But let's say for some reason eta is huge. Well, when I say huge, I mean not like a million, but let's say relatively huge. My question is, okay, forget the value, exact value of eta. When I do this, when I do the gradient descent, and if I'm starting here, where will I be? Will I be on the curve? Will I be on the line, on the slope?
On the line.
Exactly. It is always on the line. But why do we say that this works? If we are on the line, our objective is not to be on the line. Our objective is to be on the curve, not on the line, right? But why do we say gradient descent works? Why? It doesn't work, right? In a way, because we're saying, look, our objective is to be on the curve, but I'm still on the line. I'm not on the curve. So does that mean gradient descent is failing me or rather failing us? நம்மள தப்பான திசையில கொண்டு போறதா gradient descent?
If the learning rate is small, then the line will be very close to the curve.
Exactly. So if eta is very small, I'm still on the line, but the line would be very, very close to the curve, right? So even though I'm on the line, I would still be very close to the curve. And then I will figure out another derivative at that point, right? That's what I would do. I'll get another line. I'll keep doing that so that I stay on various lines that touches the curve. That's the whole idea. இதுல, I mean, just out of, it's an academic question. இதுல பிரச்சனை வரணும்னா எப்படி பிரச்சனை வரும்? So let's say, let me put it this way. If I know that this section of the curve looks like this, all right? Can eta be large? This section of the curve. I'm just showing, right? இங்கேந்து இது வரைக்கும். Or let me just switch to presentation mode. Give me a moment. I'll use a.
We see you can use laser in that normal mode too.
Sorry, say that again. What can I do?
You can see a watermark icons on the left bottom. Can you scroll
Pointer
the
option. Yeah.
Okay.
Correct. You got it. Yeah. Thank you. So let's say I'm on this part of the curve. Okay. My question is, we'll compare two parts. Okay. This part of the curve and then this part of the curve. In which case can eta be larger?
Second case.
You mean this case or this case?
No, that
I'm calling this as a flat portion. I'm calling this as a curved portion. Okay. In which portion can eta be larger? The flat portion or the curved portion?
Flat.
curved portion.
Why curved? So you're saying that eta can be large here. Is that what you're saying? Now somebody said flat. Those who say flat, what is your argument? So if you're saying eta can be large here as compared to this portion of the curve, my question is why?
In
when the
flat
curve is
portion,
flat, the
the line
line
and curve
lies on the
almost
curve.
same. Right?
Sorry, I think two people are talking. Was it Sabarishan? Sabari, was it you?
Yes, we see.
Okay,
So
go
I
ahead.
was saying like in flat portion, the line and curve almost are on the same path
Okay.
compared to the curved portion. So even if eta is large, there will be no much impact compared to curved portion.
Okay, Rajeshwari, did you get it?
Yes, please.
Puridiliya? Because here, if eta is huge, then what happens is due to the curvature, you're still on the line. So you would probably be here if eta is huge, right? Because let's say you draw a line like that. Eta is huge, na inga vanduruvom nama, illaya? You will not be on the curve. Whereas here, even if eta is huge, yes, you are still on the line. But the fact is that the line and the curve are kind of kissing each other here. So you don't have a problem. You're on the line, you're also on the curve. All right. Okay, now. So I hope you understand the value of eta. It's the learning rate. So in fact, when we do gradient descent, eta need not be constant. Eta can vary too, right? But we're not doing all that stuff. We're keeping eta constant. So when I say eta varying, eta can vary as you descend down the, when you do the gradient descent, when you try to reach the valley, you can change eta too, and eta can vary based on the gradient, for instance. Okay. All right. Now, so let's go back to the Excel. So here we have the formula. This is the previous weight, eta times the derivative. Of course, here it's one variable, but then there's a possibility that you can have multiple features, which is what we're dealing with now, W1 and W2. Now, can somebody tell me if this is the learning rate? We'll just focus on this row, okay? I'll just highlight it so that we all know which row we are dealing with. We are dealing with this row. Now, can you tell me how would we calculate the revised W1? So here is the original W1. Okay, a minute. I'll just, okay, here is the original W1. And there is a learning rate. Learning rate is, okay, let me just do this so that we can see all of them in a, Let me remove cost minus lowest cost. I don't need that. Just give me 1 minute, folks. It takes a while to. A lot of rows here. Takes a while to save. Okay, meanwhile, while it saves, can somebody help me with an expression to calculate the revised W1?
Revised W1 is equal to W1 minus gradient of W1.
Think,
Gradient of X1.
think. Go back to this formula. Go back to this formula. This, of course, is one variable.
Multiplied by the learning rate. Sorry.
Correct. So the revised W1 would be the original W1, which is E2, multiplied by R2 is the learning rate, multiplied by L2. L2 is the gradient. Okay. Now someone else can tell me what would the revised W2 be?
W2 minus learning rate into gradient of W2.
Exactly. Correct. So the original W2. So if you look at this, it says F2. What's F2? Let's see what's F2. F2 is the original W2. That's why we started. That is it. Yeah. Minus M2 into R2. R2 is, of course, learning rate. M2 is the gradient of X2. Okay. So what we're doing is now we have the revised W2, which I'm plugging in. So if you look at the next row, this is nothing but the revised. This number, this is actually S2 T2, right? So if you look at this formula, it's S2 and T2, and I repeat the same process again. Okay, I repeat all the way. I do it about 50,000 times here. Okay, now what I'm going to do is I'm going to change this to say -1 and -2. Let's save this. It's doing some calculation, folks. You can see that here at the bottom, which is why it takes some time. All right. So, okay, now if you look at this, -1, -2, I start with -1 and -2, and then this is my lowest cost. And if you look at, this is the final W1 and W2 after 50,000 iterations. This is the final W1 and W2, and the cost is, here's the cost, which also happens to be the lowest cost. Okay. I'll go all the way to the top. Now this can be something else as well. So for example, this could have been 2, and then this could have been 2, 2. Let's see what happens in that case. Just give me a folks. Sometime, folks, it's still doing some calculations. Should be done now. Another second or two. Yep, here we go. So let's see what happens here. This again is this is the, I mean, what I'm calling it as the lowest cost. And here are the revised weights after 50,000 iterations. And of course, it just so turns out that this is the cost, and it turns out that this is the lowest cost as well. Okay. Now, the key question here is, when do we stop? How do we decide when to stop? Because if you think about it, I got various lowest, so-called lowest costs here, right? It all depends on what value I plug in here. If it's 2 and 2, I got something else. If I start with, say, 2 and minus 2, for instance, all right, let's do that. I'm going to save it. It's doing some calculations. 74%, 93, 94. We should almost be there. There we are, 100%. So if you start from 2 and minus 2, I get a different lowest cost, which is different from what I got earlier. So the question is, and that's the tricky question too, how do we decide when to stop? That's number one. Number two, I'm going to ask a related question. It goes back to this. Can you help? Okay, this was the first order derivative. Can you derive the expression for the second order partial derivative with respect to Wj? Can you do that? You can, here's some clue. You can use this as a clue how to calculate the second order partial derivative with respect to Wj. You use a pen and paper and figure it out. I want an answer in terms of y cap, and xj. I'm sorry, y cap, yeah, y cap and xj. Y may not figure. Let's say y cap and xj, whatever. Just figure it out. I don't want to see the sigma w dot x and all that. Make it easy for me. Y hat, y xj. So you could have called this as y hat minus y times xj. Calculate the second order partial derivative. Is it so difficult? At least somebody get started, and why don't you just speak as you compute so that we know what you're trying to do? Somebody, why don't somebody volunteer? Out with it. Come on.
We see minus xj square
Okay, minus xj squared. Minus xj squared. Okay, go ahead.
into 1 minus y hat
Okay.
into 3y hat minus y hat the whole square.
அவ்வளோ காம்ப்ளெக்ஸா வருது. Okay.
We see x1 square into y cap into 1 minus y cap.
You mean xj square, you mean, Ilya?
Yes.
Xj square into y cap into 1 minus y cap. Okay.
Yeah.
I think you're right. Anyone else? Anyone else who got the same answer as Kirtana got? You're still struggling, is it, others? Okay, let's do it step by step, folks. Here is the first order derivative. You're going to calculate the second order. With respect to wj, can we treat xj as a constant? Yes or no? Either you say yes or you say no.
SPC.
Okay, yes. So xj goes out. So what are we going to do? We're just going to calculate the derivative of the partial derivative of whatever is there inside this, correct? Now, can you tell me, let's split that into two parts. The partial derivative of this minus the partial derivative of this. For one data point, what is the partial derivative of this?
0.
0, correct? Because we already know the value of y for that data point. So which means that's 0. So you just need the partial derivative of this, correct? With respect to w, of course. Now, this is something that we already know, don't we? We know how to calculate the partial derivative of this expression, which is nothing but y hat into 1 minus y hat times xj, correct? This is y hat into 1 minus y hat times xj. But remember, we had already taken another xj out, correct? Before we calculated the second order derivative, we'd already taken this xj out. And then while calculating the partial derivative of, okay, let me add the pointer, make it easy. All right. So we'll already taken this xj out, and then we were calculating the partial derivative of this expression. This was 0. We try to figure out the partial derivative of this, which is nothing but this. So this is y hat into 1 minus y hat times xj. I already have another xj, so it is y hat into 1 minus y hat times xj squared. And that's what Kirtana said, right? Good job, Kirtana. That was perfect. So now, so it is y hat into 1 minus y hat times xj squared. So coming back, what does y hat into 1 minus y hat xj squared, or rather in this case, a second order derivative mean? What does it mean? It defines we discussed this, right, a while back. What does a second order derivative mean?
Defines the curvature.
Exactly. So if it turns out that this is very small, this curvature is very small, it means that we are kind of close to the valley and we are roaming around in that valley, right? If this curvature is huge, then we are doing some major, we're trying to, okay, let me put it this way. The curvature should be small and so should the gradient be. So it's like you've already come close to the valley, the gradient is almost 0, and then the curvature is small. So effectively you're roaming around in that valley, correct? That's what a valley is all about, right? So let's do one thing then. Let's calculate. So here we go. I haven't calculated it here, but let's calculate it. So here is y hat, 1 minus y hat. I'm going to calculate the product of y hat into 1 minus y hat times, let's say, x1 squared. What am I? Something is wrong. Wait. Y hat into, what's wrong here? Something is wrong with Excel. I think it's taking a while to, I'll fix this calculation and I'll populate what I call as a second order derivative so that we know how curved things are. Okay. Now, see, the reason why I brought this up is I'll give an example here. Now, can you tell me one thing? Y hat and 1 minus y hat. When y hat is, say, close to 1, can you tell me what is y hat into 1 minus y hat? Let's say y hat is close to 1. What is
0.
y? Close to 0, right? So what you would find is as you get closer to your, your target classification, you'll find that y hat into y minus y hat is close to 0. You'll find that, okay? So which means the curvature isn't the same. In fact, what you will find in this case is as you go closer to the valley, it's a huge valley is what you will find, because there's a lot of space in that valley where you can play around literally. You'll understand that significance if you were to, I strongly recommend that you solve this problem where you try to figure out the minima, play around with this, you'll get an idea. I'll fix this column so that you folks can understand what I meant by the second order derivative. But let me give another example so that you get a sense of what I'm talking about. So let's say the function is, let's say the function is x squared, sorry, plus y squared. Can somebody tell me what is the second order partial derivative of? So there are two partial derivatives, of course, but what is the second order partial derivative of x squared plus y squared? What are the two partial derivatives? Second order.
It's 2.
2. What does it mean then? Okay, we know it's 2 now, but we've started interpreting the second order partial derivative as a curvature. So what does it mean?
The curvature is constant.
Yes, the curvature is constant. So which also means, okay, of course, this is a bad, this is 2D, of course. So so the way it will look like is like a spherical bowl. Right? Just imagine that way, almost like a spherical bowl. And you'll find that the curvature, it's like, think of a circle. A circle has the same curvature throughout, right? So likewise, if you look at a sphere, the sphere also has the same curvature throughout. So there is no scope for different curvatures where you can roam around a lot in the valley. No, the way it'll work is you'll come down to the lowest point and then there you are stuck there. You're there, that's it. You can't roam around. But let's say, had it been something like this, then from this point to this point, if you look at it, this is of course a cost function. The cost hasn't changed much. It's pretty much the same throughout, almost the same throughout. And yet, if you look at, and let's say this is the W, I'm just calling this W. W can vary from this all the way to this number. Now, can somebody tell me what does it mean from an optimization perspective? If W can vary from this all the way up to this, and if cost function, or rather if the cost doesn't change too much, what is the implication for optimization?
Close to minimum.
Sorry, Mugundan, say that again.
It is close to minimum, we see.
Okay, but what is the implication for optimization? So let's say Mugundan is doing optimization for this function. And let's say someone else, Rajeshwari, is also doing an optimization for this function. So let's take this example, folks. Two functions. This is function 1. This is function 2. Now, Mugundan and Rajeshwari have started doing optimization for function 1. And likewise, Mugundan and Rajeshwari, they start doing optimization for function 2. Okay. Now, in one case, as I said, with function 1, the curvature is such that it's constant throughout. You can't, I mean, there's not much scope for you at the valley. You got to that point, that's about it. There's nothing that you can do. You're stuck there literally. Here, this is the minimum point, no doubt. But it's a pretty flat region. It's like the Kashmir Pallataka. It's pretty flat at the Pallataka. Of course, there's minor deviation because this is the lowest point indeed. My question is, what is the implication from an optimization perspective? Two people are doing
For first
optimization.
function, both will get the same W value.
Okay.
And for the second one, they may get different W values.
Why different?
Because between the flat region, for every W value, will be getting lower cost function.
You see, the point is, this is still the lowest cost, right? This is still the lowest cost. Now, Mugundan and Rajeshwari are attempting to reach this lowest cost. They're trying to do the same here. My question is, from an optimization perspective, would there be a difference in the way the weights are figured out when it comes to 2 as compared to 1?
I think like there will be more change in weights in function 2.
More change in weights in function 2, or more change in weights when it comes to...
More minor deviation.
What do you mean by more minor deviation? It can be minor deviation, or it could be more deviation, right?
And like around minimum, there will be many values.
In 2 or 1? Okay, let me ask this question. So let us say Rajeshwari starts from here, comes all the way down. She almost reached here. She tried some 100 iterations. She didn't see much change, too much change in cost. She may choose to stop here. Now, Mugundan might start here. Mugundan comes all the way down. There's a super change in cost. He's happy, he's happy, he's happy. Now it gets very flat. Then he says, look, I've tried so much. Enough is enough. I will stop here, right? Now, my question is Mukundan wrong? Is Rajeshwari wrong? Or are both of them right? That's question number one. Question number two, do you see such a thing happening here? Where Rajeshwari, let's say, starts here. Mukundan starts here. They start descending down the curve. Do you see Mukundan and Rajeshwari reaching a different point in curve 1? When I say different point, I mean a different lowest point in curve 1 as compared to what happened in the case of curve 2?
No, we see.
No, correct? Because it is evident. Your logic would be, am I getting better? Here I don't get better. I stop. Because at this point, your cost will start increasing. So you would have stopped here, correct? Now Raji comes down. My cost is decreasing. Wonderful. Oh, here, the cost starts increasing. I stop here. So both Mukundan and Rajeshwari would have reached the same point and they would have stopped there. But when it comes to this curve, Raji comes down. She reaches a point where it looks like as though it is the minima. Why? Because there's not much change in the cost. There is some change, but not much. Now the question is, you have to stop somewhere, right? So Raji thinks, okay, look, I have done 500 iterations and the cost hasn't changed much. It has changed by an amount of, say, 0.0001. And Raji says, enough is enough. I don't want to proceed further. Likewise, Mukundan starts here. He goes down and then he does something similar and he stops here. So don't you see that in this particular case, Raji and Mukundan will get different weights, W. Are they wrong? Are they?
No,
No,
we see.
VC.
They're not wrong. It's close, correct? You got to stop somewhere, right? So it's just that according to their logic and algorithm, they stopped at a point which they thought was reasonable, okay? So when will this happen? That's my question. This will happen when your curvature, I mean, your gradient is almost 0. If you look at it, the gradient is almost 0. And then you have, the curvature is also 0, isn't it? You see that? The gradient is 0 because you've reached a flat surface, almost flat surface, but then there's no curvature too. Here, if you look at it, think about it. What is the gradient here? At the point that I'm showing, what is the gradient there? Or slope? This is because it's 2D. Let's call it slope. What's the slope there?
0.
0. Curvature? Is it 0?
No, VC.
It is not, correct? Why? Because the moment I move a little bit, the slope is going to change. Correct? That's what the whole deal is all about. You know, when you have a function like x squared plus y squared, the curvature is constant throughout when you move along that surface. But here, the gradient is 0 and the curvature is also 0. So which means this is a nice little valley that you can roam around, literally. So you can have a lot of weights, each one of them giving the right answer. Nothing wrong about the weights. Okay. So this is the learning. Any questions?
VC, I have a question.
Go ahead.
Initially, you said like when we have higher learning rate, will be the point will move to the line.
Correct.
Does it actually go out of the graph?
Why not? It can, right? So for example, let us say I draw a line like that. Just assume this is the point. And if eta is huge, I can come all the way up to this point. Now I'm completely stuck, isn't it? There's no way I can go back to that curve. Correct? So which is why it is extremely important that you calibrate eta. In the sense, if you know a function is very curvy, keep your eta very, it should be close to 0, isn't it? Right? Because otherwise you might lose that curve completely, the one that you were targeting. Right? So it is possible that you might miss that curve completely, or the graph completely, or the surface for that matter.
Okay, sir.
Anything else? All right, if there isn't
Easy.
anything, yeah, sorry, who was that? Madhumita, is it?
Easy.
Raji, go ahead.
Yes. In function 2, the point you say we have stopped, can we tell it as a local minimum?
It is not a local minima. I'll tell you why. When we say local minima, it is something like this, Raji. So it's like, sorry. This is a local minima, right? And this is global. Now, this is not a local minima. It is just that you've stopped because you don't want to see. It's an algorithm that is running, correct? Now, let's say, go back to this, and let's say this is the cost. You remember I was calculating a cost diff. Look at this cost diff. Pretty much no change, isn't it? Very, very minor change between one iteration and the next. Now, you might choose to stop because look at the cost diff. There's no cost diff, literally. Not much is changing. Now, somebody might say, no, let's continue. Let's continue. But then the question is, how far are we going to continue? You'll have some logic, right? Correct? You might say enough is enough. I'll probably look at 6 decimal places. If the cost diff is consistently less than 0.00000001, then I'll stop. That could be your rule, your stopping rule. Now, Mugundan might have another stopping rule. He might say, look, I will have a rule where the cost diff has to be less than 0.00000001 100 times. So as long as it's the difference between the previous cost and the current cost is less than 0.00000001, 100 continuous times, I'll stop. Now, that doesn't mean he has reached a local minima. That doesn't mean that you have reached a local minima. You understand? It just means that you have stopped. Puriyada.
SPC,
When
understand.
will that happen? That will happen when you have reached a surface that is almost flat. Right? Here, it was curvy. அது உன்னை புஷ் பண்ணிக்கிட்டே இருக்க ஏன்னா நீ இங்க இருந்தா அடுத்த ஸ்டெப் இங்க போவ you will come all the way down. You don't have a choice. And the moment you breach this point, you would have increased the substantial, your cost would have increased. So you say, look, I'm not going to go further. I'm stopping there. But here, that is not the case. Because here, as you go down that valley, it gets very, very flat. But that doesn't mean it is perfectly flat. This is still a convex function. Let's be very, very clear. 1 is a convex function, 2 is also a convex function. But the only difference is in case of 2, it gets extremely flat before you reach the lowest point. In case of 1, the curvature is the same throughout, which means from one step to another, you make a lot of progress because of the curvature. Here, from one step to another, you may not make a lot of progress. So you decide yourself. போதும் இதுக்கு மேல நான் ப்ரொசீட் பண்ண விருப்பப்படல அப்படின்னு நீ டிசைட் பண்ணிடுற. But that doesn't mean it's a local minima. புரியுதா?
Understand this.
Okay, wonderful. Anything else? Okay, wonderful, folks. Thank you for joining. We will meet again on Friday. Thank you.